Hey everybody, welcome to today's lesson and our brand new unit, which is going to be all about the periodic table of elements. Now, this is one of those things that is highly recognizable. Everybody comes into chemistry thinking, ooh, I'm gonna have to memorize the periodic table of elements, and this course is gonna be so hard because it looks so complicated. Well, we're gonna start today kind of unwinding or unraveling this periodic table and kind of showing you it's not that complicated. And also, don't worry, you don't have to memorize it, okay? So as you can see here, I have a beautiful color-coded diagram of the periodic table. We're going to eventually color code our own periodic table just so you guys also have it color-coded. But again, this is that very recognizable image of the periodic table. Now let's go ahead and dig just a little bit deeper. So I want to first start off the conversation with something that we've already learned, which is our Bohr diagrams, and kind of sketching through those Bohr diagrams to help us see what these elements have in common with one another. So let's go ahead and first start with our Bohr diagram of lithium. Lithium is element number 3, okay? And if you look at it, it has a total of 3 protons, and it has a total of 4 neutrons, okay? And that means that if it has 3 protons, it has to have a total of 3 electrons. 2 electrons in the first energy level and 1 electron in the second energy level. Let's go ahead and take a look at beryllium. Beryllium has a total of 4 protons. It is element number 4, and its number of neutrons, its mass number is 9, so it has 5 neutrons. That means if it has 4 protons, it has to have 4 electrons, 2 in our first energy level, and 2 in our second energy level. And then let's go ahead and take a look at boron. Boron is element number 5, so it has 5 protons. And if you were to look up the mass, it has a mass of close to 11, so therefore it has 6 neutrons. It contains 2 electrons in the first energy level and a total of 3 electrons in the second energy level. Now, these 3 atoms are all in the same row on the periodic table. And so why or what makes them organized in that way? Why are they organized in the same row? What do these 3 things have in common? Well, if you look at them, they don't have the same number of protons or neutrons in common, and they don't have the same number of electrons in common. However, if you notice, they do both contain only a total of 2 energy levels, okay? And that's going to be our organization factor. That's what is going to tell us what they have in common. So these things in the same row are in what we call periods, okay? That's what we call the rows of the periodic table. Now, how do I like to remember that left to right, the row is the period, are called periods? If you think about writing out a sentence, it ends in a period. You write your sentences from left to right, okay? Now, periods, again, are the horizontal rows, okay, horizontal rows, okay, which contain the same number of energy levels. So all of these elements, lithium, beryllium, and boron, are all in period 2 on the periodic table. And how many energy levels do they have? They have 2. Okay, let's now take a look at the column of lithium, sodium, and potassium. Okay, now interestingly, lithium, sodium, and potassium, okay, are all in column number 1. So let's go ahead and take a look at the Bohr diagram for sodium. So sodium, again, has it is element number 11. So it has 11 protons, and it must have 12 neutrons, as its mass number is 23. So now let's take a look at the Bohr diagram for the electrons. We have 2 electrons in our first energy level. We have 8 electrons in the second energy level. Okay, and we have 1 electron in the third energy level. Okay, let's take a look at potassium. Okay, potassium is going to be element number 19. So it has 19 protons, and its mass number is 39. So it has 20 neutrons. Let's go ahead and sketch in our electrons. In our first energy level, there's always 2. In our second, there's 8. 7 and 8. In our third, there is also 8. Okay, and in our fourth, we have a total of 1. So looking at these, this column from the periodic table, what do all 3 of these have in common? Well, I think to best see what they have in common, it's best to look at their electron configurations. So sodium's electron configuration is, I'm sorry, let's do lithium's first before I do sodium's. So lithium's electron configuration, okay, is going to be 2-1. Sodium's electron configuration is 2-8-1. Okay. Potassium's electron configuration is 2-8-8-1. So looking at each of these, what do these 3 have in common? Well, you may or may not notice just from glancing at this, at their last energy level, or what we call the valence electron shell, each of these contains only 1 valence electron. Okay, so these contain the same number of valence electrons. Okay, just the 1. And so they all belong in what is called a group. Okay, so let's go ahead and jot down the definition of groups, or sometimes we also like to call them families. Okay, so groups or families. So groups, okay, are going to be the vertical columns okay, which contain the same number of valence or outer shell electrons, okay? So we have our periods and we have our groups, and that's how our periodic table is going to be organized. Now, it is a little bit trickier to just say, oh, this is group 1, it has 1 valence electron, and I'll talk a little bit more about that as we get to the periodic table, as we get back to the periodic table. All right, so now that we know about groups and families, let's talk a little bit about the history of our periodic table. So in the 1800s, okay, or I'm sorry, in the mid-1700s, that's when chemists started actively discovering elements, okay? So in the mid-1700s, we started discovering and identifying and classifying elements and understanding that they were made up of just one substance. But it wasn't until a century later, or around 1896, where we started to kind of to organize them into this periodic table structure. Okay, and so our Russian chemist Dmitry Mendeleev, who is considered the father of the periodic table, okay, is the first person to come up with a version of the periodic table. Now on your screen, and if you're following along in the notes sheet, this image is there too, okay, this is Mendeleev's version of his periodic table, okay? Here's what's really, really cool about his periodic table. Notice that there are things that are filled in, and notice that we do see things that we already recognize, like hydrogen and lithium and beryllium and carbon and nitrogen and oxygen and fluorine and so on and so forth. But notice that there are some empty blank spaces also. Now, what was particularly amazing about this is he left these spaces for atoms that he predicted would have the same chemical properties as the other elements that he's grouped them with. Additionally, he was able to not only predict their properties, but also predict their masses, okay? And so as we later discover elements, right, into the 1900s, or even in the 2000s, as we're finding more and more, we actually realized that Mendeleev's table, he predicted all of these elements existed. Now let's take a look at the table. How was his table organized? Okay, and I also want you to notice something also really interesting. Okay, notice how he predicted helium, or I'm sorry, hydrogen, but he didn't predict helium. He didn't predict neon or argon or xenon or anything that belongs in that last column of the periodic table. And when we circle back in just a couple minutes, I'm going to talk about why. Okay, but let's take a look. How was his table organized? Or rather, let's look at some of the commonalities. Now notice he has beryllium, boron, carbon, oxygen, nitrogen, and fluorine all here listed in a column. But if you look back at what we just talked about, those are actually all things that belong in the row or in the period, okay? So his was organized, instead of being flipped this way like ours, his was up and down. But how was his organized, okay? So Mendeleev organized by mass and chemical property. Okay, mass and chemical property. And what does it have in common with ours? Notice, as I just mentioned, like I said, it is still organized into that same period. And if you look at, like, let's say fluorine, chlorine, bromine, and iodine, it's still organized into that same group. So it still had similar groupings to our periodic table. Okay, now how is our current periodic table organized? Well, our current periodic table is organized, our table is organized by atomic number. Okay, by atomic number. And it's increasing atomic number. Okay, and of course organized into groups and periods, as I just mentioned. All right, one last thing that I want to do with our first discussion is I want to talk a little bit about some of the specialty groups that exist on our table. Now, I have color-coded these groups for you, and I've also labeled them up top. So notice on the screen that there's group number 1, group number 2, groups 3 through 11, group 17, and group 18. The remainder of the groups on here aren't particularly important for this course, and we'll talk a little bit more about why that is tomorrow, as well as the lanthanide and actinide series, which fall below the periodic table. Again, not something we heavily focus on for this course. You'll also notice that I labeled the periods, period 1, 2, 3, all the way through 7 at the bottom. Okay, so let's take a look at some of these specialty groups. Now, group number 1, lithium, sodium, potassium, rubidium, cesium, and francium. These are our alkali metals, They all have 1 valence electron. Let's write down an example too. An example would be sodium. Okay, they all have 1 valence electron. They are extremely reactive. Okay, now you might be saying, wait a second, I eat sodium in my diet. You're telling me it's really reactive? Heck yes, it's really reactive. I'm going to include a video of the alkali metals reacting in water below on this post. So if you do want to watch that, check it out. It's super cool. Okay, they only exist in compounds in nature. They only exist in compounds. So you can actually get pure sodium or pure lithium, but what's going to have to happen is it's actually stored in oil to avoid it from reacting with the air or anything else that it comes in contact with, because again, it's really reactive. So they only exist in compounds. Okay, group 2, the alkaline earth metals. These aren't really that exciting, unfortunately. An example is magnesium. Okay, and they have 2 valence electrons, and that's really all about that you need to know about them. They have 2 valence electrons. Now, groups 3 through 11 are some of my favorite. these are called transition metals. Now, what's really, really cool about transition metals is anytime you see those really beautiful colored solutions in lab, those are specifically made with transition metals. So, for example, if you take sodium chloride or NaCl and dissolve it in water, it's going to be clear. There is no color to that. Why? Because sodium is an alkali metal. It's not a transition metal. Those transition metals are the only ones that form those colored compounds. So these form colored aqueous solutions. Okay, and they also form multiple charges. Form multiple charges. Okay. Group 17 are the halogens. Okay, halogens, they have 7 valence electrons. An example of a halogen is going to be chlorine. Okay, they have 7 valence electrons. These are extremely reactive. Okay, extremely reactive. And they all exist in diatomics in nature, right? So remember we talked all about those diatomics. Remember we said that the diatomics were H2, O2, F2, Br2, okay, Br2, I2, N2, and Cl2. These exist only in diatomics in nature, okay? And yes, oxygen and nitrogen and hydrogen are not part of that group, but fluorine, chlorine, bromine, and iodine all exist in diatomic in nature. And the last group that we have are the noble gases, group 18. Now, these are so cool. And remember, these are the ones Mendeleev did not discover, right? He didn't predict these at all. These are really special and they're considered noble because they have a full valence shell. They have a total of 8 valence electrons, with the exception of helium, which has only 2. But remember, your first shell can only hold a maximum of 2 electrons. They are what we call inert, which means that they are stable and unreactive. Okay? And the last thing to note is that these are the only things that exist as monatomic in nature. Monatomic. Remember, if diatomic means made of 2 atoms, monatomic is made of 1 atom, okay? Now, why did Mendeleev not discover these or predict these? Mendeleev's table was based on chemical properties or observing things react with other things. If these are inert or stable and unreactive, then he didn't see any reaction with these group 18 elements. I'm sorry for the length of this lesson. This periodic table stuff is so fascinating and awesome. I hope you enjoyed the lesson. I hope you guys have a fantastic rest of your day, and I will see you guys tomorrow.